Yeah, so my name is Aymeric Damien. I'm an ML engineer at Snap, where I work on inference and training pipeline optimization. And today I just wanted to give a talk about our work on training large-scale recommendation models with TPUs. And first, let me give you an overview of like Snap. So actually, what are we trying to do at Snap ad ranking? So basically, we're trying to predict the likelihood of a user to engage with an ad. And to do that, we train different models, and it's pretty important because the closer the prediction is, the better it is first for the user, so that we can have relevant ads to show, then for the advertiser to get more advertiser value, and then for Snap for our revenue. And yeah, so this prediction is actually used by the ad auction systems that check many parameters together, such as the advertiser budget, the budget pacing, the max bid, etc. And when we need to show an ad, this ad auction system will basically choose which ads to show. And that's pretty important, as I mentioned. And then once we show an ad, we basically check if the user engaged or not, and that's how we generate labels out of that. And our ranking system is pretty straightforward. We have a light and heavy ranker. So one retrieval phase, when we try to cut down with cheap and accurate models, the total number of ads we have to rank, and then we have much more heavy models, but that are much more accurate, where we really try to fine-tune the prediction and get the best result. So our models, they have thousands of numerical features, hundreds of categorical features. Our architecture is also pretty straightforward. I mean, in terms of recommendation systems, so pretty popular, DCN, DCNv2, PLEs. And our infrastructure is mostly based out of Google Cloud, but we have also some part on AWS. And a quick word on ML hardware. So we historically trained with CPUs, asynchronous training, but now we're migrating to TPU. And on the inference side, we have a mix between CPU and GPUs. Also, I wanted to highlight some things I believe are really challenging with recommendation systems. So first, our dataset actually has a lot of categorical features. So we need pretty large embedding tables. And if you're not familiar, embeddings actually represent discrete ID features. ID feature as dense vector in a low dimensional space. So for the embedding lookups, they're actually pretty memory intensive. And I would argue that actually recommenders have been a little under-investigated by academia, and maybe one reason is that there is a lack of public data set, unlike computer vision or NLP. And also for this data set, for example, Criteo is pretty famous, but the number of features is like around 39, so it's like way different from the amount of data we deal with. And I think that makes the entire like research pretty hard to reproduce. And as such, there is not too much focus on software integration that really focus on recommendation systems. And as a next consequence, actually specialized ML hardware has really always focused on like large matrix multiplication, but actually the recommenders have other additional requirements, such as fast embedding lookups, large memory, high memory bandwidth, and so on. So now I want to talk a bit more about our TPU integration and the benchmark we ran. So first, for those who don't know what is TPU, TPU is actually Google custom developed ASICs for deep learning, and it's actually it came actually pretty early on. It's back to 2015, so 7 years ago. And the V5 is supposed to come, I think, this year. And why use TPU for recommendation system? First is that they have actually large memories. A TPU V38 has 128 gigabytes of RAM. So that's quite a lot, especially compared to one GPU. And it also have high bandwidth. Second thing, there is fast chips interconnect. And third is that they also provide a really good TPU embedding API that have native and optimized solution for embedding-based operations. So it's really fast and efficient embedding lookups, and that's really what we need for recommendation systems. And then it also supports sharding. So those very large embedding tables can be sharded across many different TPU cores, so that even if you exceed this 128 gigabytes, you can easily shard your embeddings across many different devices. So if you deal with very large embedding, that's very useful. Another point that's pretty, I think, good with TPU is that they have BF16 matmul acceleration, what I call under the hood. So you don't not like GPU where you need to specify your weights as a BF16. All these BF16 matmul are done under the hood, so you can just define everything as FP32, and then it's just working pretty well. And last, it's easy to integrate with TensorFlow, and it also has a good general availability. So that's cool if you want to train at scale. Our TPU integration, we needed to refactor some of our TF code base, migrate to this TPU embedding API, and we also faced some challenge around the IO pipeline. So we used to train on a CPU machine that was only like 8 cores, so the throughput per machine was actually pretty low. And then we switched to TPU with that much higher throughput. So we really needed to optimize the IO pipeline so that we were not IO input bound. And we also migrated from asynchronous to synchronous training, which is the default strategy with TensorFlow. Then there were some challenges. So running TPU is definitely not as straightforward as using GPUs. I would say that optimizing GPUs is another topic, but at least just running on GPU is much easier compared to running TPUs. Some ops are not supported, and we also needed to tune our training because we migrated from asynchronous to synchronous, so there were some hyperparameters that needed to change. And last, there is also some scaling issue I will come back to. So now I wanted just to share some results on our benchmark. So first, actually we saw really great performance boost by migrating to TPU from our original CPU training, so up to 250% throughput for standard model. And the heavier the model gets, the better the performance boost. So for heavy model, we could see up to 600% higher throughput, and actually a huge cost reduction by 87%, taking standard Google Cloud pricing. And then we also compare with GPU, and then we found also really great result with TPU. I just added a note there. So we use an optimized image for the 800 GPU, but we didn't have how to say, like, the best optimization. So recently, NVIDIA released this huge CTRTF plugin that's doing something similar that TensorFlow did with TPU embedding API, that's speeding up embedding lookups. So we yet have to benchmark this, but so far without this optimization, TPU really beat the 800. And and one last word on TPU scaling. So we saw actually some scaling issues, and it's not necessarily only linked to TPU, so there is one famous ML-perf competition where people try different ML hardware and see their performance on different tasks. And for the recommended system on DLRM, actually both TPU and GPU were heavily bottlenecked the higher the number of cores. And this may be due to synchronous training. It's a lot of basically systems were designed with computer vision in mind. In computer vision, you have one batch is exactly the same size, but in recommendations that may not be true because we have a lot of variable length features. And for example, one user might have the not seen any ads, so there is no embedding lookups to perform. And what if one user saw 100 or 1,000 of ads? So we have thousands of embedding lookup to perform to that user. So then suddenly you have many more computation to do. So this worker might slow down the entire all radius process. And just last words on future work and the conclusion. So even though TPU works best for us right now, we actually really try to optimize for each type of hardware. I think it's a really competitive and fast-moving environment. So the idea there is that we really want to future-proof our training system and then just switch to whatever works best in the future. And there is a ton of exciting new ML hardware coming. So I mentioned the TPU V5, but then there is also Intel Sapphire Rapids, and I think it looks pretty good because they are going to leverage the integrated graphics core for the CPU of the CPU to speed up Matmul, and also they're going to have HB memory, so high bandwidth memory. So that should be actually pretty good for recommendation systems. Last, there is a new NVIDIA H100. This actually has even better performance than 800, so really looking forward to benchmark this. And last, there is also Habana, which is an Intel company, and they're focusing on, similar to TPU, really focusing on deep learning. And they just released, I think 2 weeks ago, their Gaudi 2 that shows pretty good improvement over 800, but what's even more important is that they are really targeting the performance per dollar, and in terms of performance per dollar, they should be pretty competitive. So a ton of interesting things. If you want to learn more, yeah, it was pretty brief presentation, so there's so many detail I left out. I added a link there so you can get more insight on how we train model with TPU, the machine learning we do at Snap for ad ranking, and also how we apply GPU to Snap for GPU inference. Cool, thanks everyone. Glad to be here.